The operational amplifier, or op-amp, is a very significant component in analog electronics. It provides a building block for amplification. Here is the op-amp page in Wikipedia, and here we have a circuit symbol for an op-amp. It has two inputs, an inverting input with a minus and a non-inverting input with a plus. And it takes this differential voltage between these two and amplifies it to the output. Now, amplification is the linear multiplication of whatever the input, this differential voltage is, multiplied by an amplification factor, A, which sets the slope of this line. Now, the problem with this is that high amplification, you can get near infinite values required for the output. So the solution of the op-amp is to limit the output beyond certain bounds here, from minus 15 volts to plus 15 volts. It only amplifies linearly in the range until saturation. Back to the wiki page, the ideal op-amp only has two inputs, but a real op-amp here has an additional set of inputs. The signal inputs are in the range of 5 volts, but these power inputs are from plus 15 volts to minus 15 volts, and these provide the power for the amplification. Now let's take a look at Paul Falstad's most excellent circuit simulator applet. So let's draw active building block op-amp, ideal, and here we have an op-amp. Let's provide it with a couple of inputs and sources, add variable voltage, and we'll say here's a variable voltage, and here's another variable voltage. As we create these voltages, you'll see over here on the right, there are sliders that adjust the actual magnitude of the voltage. Now we'll add a couple of resistors. Add resistor R. Here's a resistor in here and a resistor in here. And now we'll right-click here to add a scope to view the output of the op-amp while we play around with the values of the input. Now take a look. If the non-inverting input is greater than the inverting input, then the output here is plus 15, the maximum positive value. If the non-inverting input is less than the inverting input, then we get minus 15, the maximum negative value. So here we see the comparator function of the op-amp, that it just compares the two voltages on its inputs and gives a maximum or minimum output based on those relative values. To get the linear response that we want from our op-amp, we need to add a wire. Here we can either do draw, add wire, or we can hit the W key, and we'll add a wire that goes up here from the output across over to the inverting input. This is a negative feedback control. And take a look at our output voltage now. Instead of being an abrupt bang bang from one extreme to the next, we get a kind of linear amplification of the difference between the two inputs. And this had me confused. How does that negative feedback work? To clarify the principles here in my own mind, I created a hydraulic analogy for the op-amp. Here is my op-amp hydraulic analogy. It's a Python program available on my GitHub site. And here we have the two inputs. This is the non-inverting input, and the other one is the inverting input. And these feed into a cylinder either side of this blue piston, and when the non-inverting input is greater than the inverting input, the piston slams to the left, whereas when the inverting input is greater than the non-inverting input, it slams over to the right. Now I'm going to pause the simulation here so I can move the piston directly with this slider and take a look at the red bar either side of the piston. And it is a valve on the right and a valve on the left connected to the plus 15 volt on the right and the minus 15 volt on the left in such a way that when the piston slides to the left, it closes the minus 15 valve and opens the plus 15 valve, whereas when it slides the other way, it closes the plus power and opens the minus power. Now, if I turn on this function line, you can see that although there's a bang-bang comparator performance beyond this limit, right in the middle there's a little linear range where the output is proportional to this input. So back to Fallstad, I've added a switch here into this feedback loop, and when the switch is open, then we get the bang-bang comparator type behavior as we expect. But when we close the switch and turn on the feedback mode, take a look at the output down here in the trace, and it's now a proportional output. It looks like a low voltage, but that's because it's automatically scaling. So back to my hydraulic analogy, we'll go to the op-amp analog with feedback, and we'll run that. And here we have the same arrangement as before, but now we have a feedback connection with a valve from the output back to the inverting input. So if I have the valve closed, we get that bang-bang kind of comparator function going on. But if I open the feedback valve, now you'll see that the output grows or shrinks proportionate with the input. In fact, if I move the inverting input to 0, then the output becomes proportionate to the input. And if I close the valve, it goes back to the bang-bang behavior. So that's my hydraulic analogy to give you an intuitive understanding of the operational principles behind the operational amplifier.